Thank you very much for the invitation. Thank you, Silvana, also for the invitation. Really appreciate it. I'm very happy to give this talk today. And so I have to acknowledge that this talk is given thanks to the Rock Deformation Laboratory, of which I am the PI here at the University of Texas at Austin. And these are some of the students that, these are the students that passed through the lab so far. And in the center here, there is Ethan Corrad, who is the first author of the paper that we're going to talk about. If you want to know more about us, go to the website here, and we will have 2 new students coming. Many of the students here are now graduated. And in the laboratory, we do have a lot of toys. Our students, they play with these toys. Our laboratory is thought to be Army Swiss knife of rock physics. The idea is to allow people to experiment and do tests to understand the physics of rocks. And here on the top right corner, we do have Ethan in front of his machine. And today we will talk about experiments performed with this machine, which is a rotary shear machine. So you will find more details about the talk I'm going to give in this paper, which came out in January in JGR, Solid Earth. And the paper is entitled Influence of Frictional Melt on the Seismic Cycle, Insights from Experimental Rock Analog Material. And Ethan worked with me. I've been co-supervising him, and Brett Carpenter from University of Oklahoma, and Judy Toro from University of Padova. The idea is to use this apparatus, which is called ECoR. ECoR stands for Energy-Controlled-Rotary shear. And the idea is to study friction and the behavior of faults by using a rotary shear machine, which is slightly different than all the other designs that we have seen so far. Caroline before mentioned that I did my master in Padova in 2008, and I did my master under the supervision of Professor Di Toro. And at the time, I did my master on using a rotary machine, which was a typical rotary machine, where the velocity and the displacement are imposed. And I will go briefly there in a few slides. I will explain you why imposing velocity and displacement might limit our understanding of earthquakes. So the ECoR, which is the machine you see here, has a long story. And it started in 2012, 2013 at ETH. And this was an idea in collaboration with Dr. Benoit Cordonnier. And we together designed the machine and built the machine. And in 2013, Ms. Catherine Rieger did her master thesis, and after that the machine stayed at ETH till 2016 without being used. And in 2016, when I moved to UT Austin, I bought the ECoR from ETH for $1,000. So then Ethan, from 2018 to 2021, worked on the ECoR, and last year, this work and future work has been supported by NSF. So the idea of the ECoR is really to combine stick slip and rotary shear experiment. And these 2 pictures are kind of indicative, right? They kind of represent stick slip on the left with Chris Marone, who came to visit the lab a few months ago, and David Goldsby on the right hand side here, who came also to visit the lab last year. And with Dave, we did also some experiments. Here there is an experiment going on. Is Dave controlling that everything runs smoothly? And Chris Marone and Dave Goldsby are for sure 2 of the most famous scientists working on the 2 aspects. On the 2 methodologies, the stick slip methodology and the rotary shear methodology, to understand friction in rocks. And now, before I start introducing, speaking about stick slip and rotary, I want to make sure everybody here is the same page, and I would like to define some quantities. So we define the friction coefficient as the ratio between the resistance of sliding of a block of rock, for example, on another block of rock, divided the normal load. And in this case, the force applied to the block is higher than the resistance, so the block actually will start moving. And while moving, it will eventually generate heat at the surface here, and the heat production has been, for example, described by Rice in 1999 and 2006 through the theory of flash heating weakening, which has been borrowed by the engineering. Another way to see this normal load and resistance, I will use these symbols right throughout the presentation. Sigma is the normal stress and tau is the shear stress. For many of you, this can be very trivial and common things, but I want to make sure everybody is on the same page. The other few things that I would like to make sure everybody is on the same page here is that whenever we try to, for example, change the velocity at which the block is moving, we typically observe either an increase or a decrease of friction, meaning the resistance is going to increase or decrease. And in this case, in this synthetic case, where the velocity is at this level here and then gets increased quickly at this point, the friction goes from this value here to this value here. In this case, the long-term effect B is higher than the direct effect A. And in this case, we will have a weakening process going on, some sort of processes or mechanism that is going to decrease the resistance of the rock. And there are several mechanisms that have been studied. Flash heating weakening is one of those, for example. So now going back to stick slip, stick slip has been a phenomenal way to study the friction instability. I cite a few studies here. There are really a plethora of studies, right? Brace and Bailey were probably the first one to apply such studies, similar studies, in the 60s. Then Dietrich, Marone for sure, Carpenter, and many, many others. And again, the typical experiment, right, is to have a load point velocity where we make the rock sliding against another rock. And then at a certain velocity, here, for example, we have 0.4 millimeter per second. And then the idea is to increase the velocity rapidly, for example, of 1 order of magnitude, and see what happens to the friction. In this case, again, we have a weakening behavior. The friction goes down from a value of 0.555 to a value of 0.54. And the stick slip idea has been very useful also in other kind of experiments to study the spontaneous slip, the fact that slip can occur spontaneously when for example, the stress is increased slowly. However, the stick slip experiments, they do have a limitation. They typically bear very small velocities and slip distances. We are in the order of millimeter per second and millimeter in displacement. So I would say sub-millimeter per second and millimetric displacement. During the year, there's been some attempt in trying to tune the stiffness of the machine, of the apparatus, which typically is a biaxial machine. So imagine a sandwich with in between a slab of rock, and then you try to push the slab of rock past the other two samples, or even one sample past to the other. And the sandwich there's a certain normal stress applied perpendicular to the direction of sliding. And what is measured is the resistance again, like shown in the previous slide. And the idea is that if you change the stiffness of the machine around such a sandwich of rock, right, you will change the behavior of the fault. And here, Lehman in 2016 show clearly that increasing the effective stiffness will change the behavior of the stick slip. Here we do have several stick slip with a certain friction increases and drops. And as the effective stiffness changes, right, such a behavior disappears. Now, the interesting thing is that the stick slip methodology bears very low velocity and displacement. And the low velocity, it's kind of a limitation, because we know that during co-seismic slip, velocities can be as high as 4 meters per second, probably, or even more. In any case, in the order of 1 meter per second. And typically, stick slip experiments cannot get to those velocities. So a slow slip rate, you know, the friction of crustal rocks is typically 0.6, as seen, for example, in the experiment in the previous slide, right? And such a friction coefficient are much higher than the slip rate, the friction that are observed at high slip rate. And this low friction is kind of, you know, support the idea that there are these weakening mechanisms that occur when the velocity overcomes certain values. And the fact that there are weakening mechanisms is also supported by a field observation. For example, the lack of thermal anomaly around faults once there is a big earthquake, right? In other words, if the friction would have been always 0.6 in the subsurface, during big earthquake, we should see an increase of temperature higher than what we observe. So therefore, in the past, people have been devising different kind of machines from stick slip and start experimenting with velocities much higher than those bear by stick slip experiments. And rotary shear tests have been incredibly useful to understand the weakening mechanisms, to understand which one are the weakening mechanisms, and how rocks eventually become weaker. I again cite a few of the people that have been working on rotary shear experiments. Tisato was one of the first ones, right, that tried to increase those velocities and go from a few millimeters per second to meter per second, right? And I cite here is a paper from 2011, which is kind of a review paper that puts together many of the others. So the rotary shear experiments, right, are excellent to go at co-seismic velocities and to get to the slip distances, which are typical of an earthquake, which are meters, right? However, the way they have been performed so far does not allow to see the spontaneous slip, the spontaneous nucleation of an earthquake and the spontaneous arrest of an earthquake. In other words, it does not allow us to see what I call the co-seismic feedback. The co-seismic feedback, the idea is that you do have an energy accumulated around the fault, and then at a certain point, above a certain threshold, you have the nucleation of the rupture, and this increases the slip velocity, and the slip velocity induces weakening or strengthening, and then this feeds back in the energy accumulated, right? At the same time, the energy transfer far from the fault into the fault through the fault zone, right, is also something that controls the slip velocity. So these two, the energy accumulated and the rate at which the energy is transferred and dissipated, right? Dissipated inside the fault while slipping, both control the slip velocity and the slip distance. And together, they control the weakening and strengthening of the fault. So in a classic rotary shear experiment, what is missing is this feedback, right? That feeds back into the rate and to the energy accumulated. As a matter of fact, some people in the past have been trying to work by controlling the energy provided to the fault and try to simulate this feedback, right? For example, Chang or Ratches and Lochner, they try to use the Roga machine, which has a spinning spinning wheel, like a wheel with a very big mass, which is accelerated and then suddenly put in contact with a clutch. A clutch is closed, and then the energy is quickly transferred from the spinning wheel into the sample, accelerating the sample very quickly. And then the energy fundamentally, which is available, is the inertial energy stored in such a spinning wheel. And then Rieger 2013 is our student from ETH, although she never really published a paper. And Spagnolo in 2012 with the machine Shiva, which is in Rome, PI was Di Toro again. So Elena Spagnolo tried to use an electronic feedback to control the nucleation of earthquakes and then control the energy provided. But you know, we 10 years ago, again in 2012, we got to a different idea to use a spring, which I'm going very quickly. Just to make again everybody on the same page, I want to show you how a rotary shear experiment look like, and I want to show you first a classical rotary shear experiment. So here we are slowly increasing the friction by maintaining the velocity constant. So we are slipping this top sample into respect the bottom sample, which are two half samples. The fault is in between here. And then suddenly you will see we will increase the velocity here in red and maintain the velocity for a certain displacement for a certain time. And as you can see here, the friction goes from 0.7 to 0.5 and remains to 0.5 for the time that the velocity is sustained, and eventually goes back to 0.7 as the velocity decreases. So again, this is a classical rotary shear experiment. And as you can see here, the velocity is completely controlled by the machine itself. The machine imposes the velocity and the displacement as a consequence, because this controls the time, right, at which this velocity is applied. And there is no feedback from the fault and from the processes happening in the fault. In other words, if the fault, for some reason, is going to fight back the movement, because, for example, a strengthening process is occurring, then the machine will simply put more energy in order to maintain the velocity constant. And such an approach has been done in the past because I think rotary shear experiments have been borrowed from engineering. And engineers, they typically design parts and they are interested in understanding how parts holds at a certain speed or for a certain distance. So this is the difference between a classic rotary shear experiment and an ECoR experiment, an energy-controlled-rotary shear experiment, which is done with this ECoR apparatus in my laboratory. And the idea is that you do have a rotary shear machine, pretty much similar to all the other ones, except the scale. This machine is extremely small. And the difference between a normal rotary shear, this one is the rotary shear that I used in 2008 to do my master thesis. And here we do have a spinning chuck, right, that spins against a fixed chuck, and the samples were in between here. And again, the velocity was imposed by this axle here. So the difference is that there is a spring clock in between the motor and the sample itself. And the results are clearly different. This is exactly the same experiment I showed you before in the animation. Here we have the friction coefficient, which is constant because we are maintaining a very slow slip velocity, imposing a very slow slip velocity. And here suddenly we increase the slip velocity, the friction goes down, but all this velocity and displacement are imposed, are controlled a priori. And this one instead is a typical experiment that we can obtain with an ECoR machine. This is this is still the friction and the velocity here, the velocity is fundamentally zero, and then suddenly some seismic precursors happen. Eventually the velocity goes down, and then suddenly a spike, and then it goes down again, and then suddenly the fault decides that cannot hold anymore the stress applied, because while this happens, the clock has been loaded. So the motor, what the motor does, imposes a continuous constant rotation to the clock spring, which is connected to the sample. So by winding up the clock spring, which is shown by Ethan here, you are increasing the shear stress on the fault, or the torque also, right, on the fault. And as you can see here, the earthquake or the velocity, right, of slip is not as smooth as the velocity obtained here, because here it was controlled. While here, the velocity is a function of the processes happening on the fault. So for this reason, we think that ECoR is a great way to study the feedback between the energy that is stored in the spring, in this case, right? The rate at which that energy is provided to the fault, and the processes happening on the fault itself. So we know that the stiffness influences the behavior, the slip behavior of a fault. And this is well known. The first one to put forward this idea was Gu and collaborator in '84 and Rice in '83. The idea is that the system is unstable when K, which is the stiffness of the elastic stiffness of the system, right, is less than a critical stiffness, Kc. And Kc is controlled by some properties of the rock, B minus A. I remind you that B is the long-term the long-term effect, I'm sorry, while A is the direct effect, is the increase of friction due to the change in velocity, while B is the change in friction after a while that the sample has slipped, after the change in velocity. And D sub C is the critical distance, is the distance that the sample takes to go from this change in friction to another steady state value of friction, right? And in this case here, for example, it was less than a millimeter. It was less than 0.5 millimeters. So this was roughly 0.4 millimeter, okay? So D sub C is the denominator here. So smaller is this, higher is the critical stiffness, and higher is the difference between B and A, also higher is the critical stiffness. And higher is the normal stress. This is fundamentally the normal stress. Is the effective normal stress, if you want. Higher is also the critical stiffness. So we know that in the ECoR machine, if we change the stiffness of our spring, we will also change the stiffness of the system, and therefore we can explore better this idea that the system becomes unstable, the fault becomes unstable when K, the elastic stiffness of our system, which is fundamentally the stiffness of the spring, right, is less than this critical stiffness. And I want to also put here forward the idea that as we have a spring, the spring energy storing the energy storing the spring or the work that is needed to load the spring, it's proportional to the stiffness of the spring, right? And the square of the distance of how much you have loaded the spring. This is the case for a linear spring, right? The idea then is that, of course, also in nature, there is a strong dependence of the slip behavior of faults with the stiffness of the rocks which are around the fault itself, right? And this is kind of the work, for example, done by Faulkner and Mitchell, right, in UK since many years now. And the idea is that the structure of the fault is fundamental to understand how the fault will behave if in a seismogenic or not way. So again, the hypothesis here is that the slip behavior and friction are a function of the stiffness of the system, and they are also a function of weakening and strengthening mechanisms. And the way that we can understand and explore such a feedback between the energy accumulated and the rate at which the energy is transferred and dissipated can be done thanks to a system which combines fundamentally the stick slip idea with the rotary shear idea. So the ECoR system, right? Okay, so this is our machine. And our machine, again, is made of a motor, electric motor that winds up a spring, a clock spring, which is very similar to the spring that you see here. We have two of them with different stiffnesses. And the torque generated by this spring is transferred to the bottom sample of these two pair of samples. And the bottom sample, which you can see here, is also connected to a tooth rubber band, which allows us to measure the rotation of the bottom sample. The top sample instead is locked and is attached to a torque cell and a load cell. So the torque cell is needed to measure the torque and eventually infer the shear stress, and then the load cell is needed to measure, to calculate the normal stress and the normal force. Okay. In here you also see other details that I'm going to show here in another slide. So fundamentally, the fault that we are looking at is the contact between this top sample, which doesn't spin, and this bottom sample, which does spin. Okay, so on the top of the machine, we have a barbell plates and dead weight holder. So we fundamentally load the fault, I'm sorry, by loading weights on top of the machine itself, transferring the stress through these linear bearings, which are mounted here. I forgot to mention that the top sample is typically hollowed to avoid that there is a point in the center which does not have any linear velocity, right? Then we have typically we use high-speed cameras to record what happens on the fault, especially when, of course, especially when we use transparent materials. We typically use a red laser to illuminate the fault, and you will see later why we do that. And we do have acoustic emission sensors, which they have been extremely important because they show very interesting results. And again, the clock spring is here and the motor is down here. So now I'm going to show you quickly a movie of how this experiment is typically conducted. And this is the friction that is increasing. And then suddenly, the fault decides to slip. And this can be repeated continuously. And you can see here in the back, this is the sensor that we use to measure the rotation of our sample. Other details here, the sample you see is being lifted. So this is the bottom sample, which spins, and the top sample, which is fixed. So before the experiment, we also have a vertical displacement sensor to see the shortening and dilation eventually of the sample. And again, on top here, we do have again a couple of acoustic emission sensors mounted very close to the fault. So why do we use PMMA or plexiglass in our experiment? So we do use plexiglass in our experiment because at the end of the day, it's a transparent material. It's a very simple material to be machined, has been used by others to study as an analog to study the behavior of rocks. And in fact, it does have an homologous temperature, which I remind you is the ratio between the ambient temperature and the melting temperature, right? Which is similar to a granitic rock at seismogenic depth. If we think, for example, of a thermal gradient of 27 degrees C per kilometer, at 17 kilometers depth, we should have a temperature around 750 Kelvin. And if we think that the melting temperature of a granite can be around 1000 Kelvin, then that will give you a homologous temperature of 0.7, which is very similar again to the homologous temperature of PMMA. PMMA are standard temperature and pressure. It melts at 400, a standard pressure at a room temperature and pressure, it will melt at 418 Kelvin. And yeah, so if we think at the room temperature, right, 293 Kelvin roughly, its homologous temperature will be also 0.7. So yeah, so the melting point is roughly 160 Celsius, you can see here. Now our samples, they are small because the machine is small. Typical rotary shear experiments are performed on samples which are 50 to 60 millimeter in diameter at least. There are some machines like Shiva or Roga, University of Oklahoma, which uses much bigger samples, samples up to 10 centimeters in diameter, so 100 millimeter in diameter. So our machine, because it's small, it cannot really hold big samples. So the radius of the sample, the top sample, can be maximum 15 millimeters, and the radius of the bottom sample can be maximum 40 millimeters. The typical normal loads that we are working on is in the order of 5 megapascal. I would say between 1 and 5 megapascal. I will show you here examples with a normal load of 3.6 megapascal. And I will show you experiments where the loading rate, the speed of the motor which loads the clock spring, varies between 0.15 megapascal per second. This is how much the shear stress increases on the fault in time, right? So between 0.15 and 1.5 megapascal per second. All the experiments we have been performing here, we try to prepare the surfaces in a standard way in order to minimize the differences due to the sample preparation. And the samples are typically prepared with a lathe. They're then polished with abrasive paper with different grits. And then they are cleaned with alcohol, which is extremely important. We had some experiment where we didn't clean the surface and the behavior was extremely different. So there is a big attention on this. Okay, this is a typical experiment which lasts 10 minutes, in which we had several long distance stick slip events. Okay, so you see here the shear stress. So if you divide this number here by 3.7, which is the normal stress, you will obtain the friction coefficient. So you see here we increase the shear stress by loading that clock spring, and then suddenly we do have events happening. And in this phase here, which is phase A, we had a torque rate, or better, a shear stress rate of 0.15 megapascal per second. So each second we were increasing the shear stress of 0.15 megapascal. Of course, the shear stress was released each time an event was happening. And we did have a couple of thermocouples, one in the center of the sample and one on the side of the sample. And the temperature raised in the beginning of a few Celsius. You can see the temperature scale here. And then kind of found a maximum and stabilized around the value. So we know from other experiments that this behavior would have continued for much longer if we would not have increased the shear stress rate, which went from 0.15 to 1.6 megapascal per second. And then what happens suddenly, right, when you increase the rate at which you're loading your clock spring, then the events are much more frequent. So fundamentally, this part here is just equal to this part here, but all the events are so squeezed one close to each other that you can't really see, you can't really distinguish them. Now, the temperature, of course, increases further as the increase of temperature in the fault will be controlled by how quickly that temperature increase can be dissipated. So because we are now dissipating more energy in a certain amount of time, the temperature raised because the heat has no time to escape, right, to be dissipated in the ambient. Now, this behavior of continuing having this very constant stick slip events, right, goes on up to a certain point where we had a runaway. And we have a runaway not only in the behavior of the slip, where we have an increase in resistance. So the peak here tells you how resistant was your fault, right? And the peak down here eventually tells you the minimum friction during the slip, right? So we do have a change in the maximum resistance of the fault, and we also have a decrease, a slight decrease in the minimum friction. Now we have to be careful because here we go below zero means that the sample was reversing. So what happens, and I will show you a movie in a few minutes. What is happening is that when the sample start developing melt, the melt lubricates the fault, so the velocity goes to 1.2 meter per second. At that point, the inertia is so high that you unload completely the spring, and then the spring eventually at the end gets to a reversal because you have overshoot fundamentally. This behavior of very high resistance goes on for a while, for roughly 120 seconds. And then suddenly you do have a behavior which is completely different. You start developing a very thick layer of melt, and that thick layer of melt is sustained, and the sample at that point deforms by creep. So there is not any more stick slip behavior, but everything is deforming in like viscous shear. So now we are going to see one of these events. Well, before doing that, I want to define again a few quantities. I want to define especially the mu SS. So mu SS, mu is friction, right? And SS is steady state. So the friction of steady state, right, is defined as the value of the friction at the minimum during the slip. Okay, so fundamentally what we are seeing here, it's a zoom inside one of these events where friction was around 1. So I guess was one event where shear stress was 3.6. So one event like this one, for example, or this one. Yeah, this box here is not really centered around. I might have moved I might have moved it. Anyway, so this, you can see the velocity, how the velocity increases at the moment that the failure nucleates. The velocity goes pretty rapidly in the order of 5 milliseconds from 0 meter per second to 0.6 meter per second. And once it gets to the maximum, the friction fundamentally stabilizes around a value of 0.15. Okay, so mu SS is that value. Now, how do we know that there is melt? How do we know that this increase of resistance is due to the fact that the melt solidify inside the fault? And also, how do we know that eventually there is lubrication decreasing the steady state friction? Well, there are two big hints, I would say. The first one is that if we stop the experiment after some of these events, or even during the creep here, the two samples are stuck. They are fundamentally attached one to the other, right? And this happens every time. So that's I would say 100% clear that this is melt. How does that melt look like? Well, we took some SEM imaging, right, of such a melt layer. We cut the sample in a half, and then we look inside. And for example, if we take here from this corner, so this corner here is this corner here, you can clearly see that there is a layer of molten material which is sometimes extruded from the fault itself, right? And this is the slipping zone going inside. Interestingly, we also did some experiment where we stopped the slipper, right, before getting to this catastrophic sequence of events where we have a lot of melt. We stop it around here, or even around here, and we didn't find the evidence of melting, right? However, if we stop the experiment a bit further, right, here, for example, where we can still take the two samples apart, then we do have evidence of partial melt, for example, this one, right? Which are, these images are very similar to other images from experiment with, for example, gabbro materials from Violet and collaborators. So how does the result, right, from this machine compare to other results? And if we take, if we extract 93 events, if you extract events, right, from all these events, we extracted 93 from here, and we compare, for example, the mean slip velocity, the average slip velocity, and the drop in shear stress, then we find that our results, which are in blue here, align fairly well with the experiment from the lab of other people, and also from natural events like the Kobe 1995 or the Norwich earthquake from 1994. Now, because we do have a spring, and we know the torque and the speed at which our sample is slipping, we can do an energy balance. We can calculate the energy flux. So we can calculate the EF, which is fundamentally the energy flux over the fault area. This is simply done by looking at the constant of the spring and how much the spring rotates, and also we can look at how much power is dissipated by looking at the torque. So on one side we do have the energy in the spring, and on the other side we do have the energy from the friction, right? And if we look at that and we and we compare to other experiments by looking the new SS, the steady state friction, which is the factor I showed you before, our experiments are very comparable with other experiments. And fundamentally, these are events taken from this phase, and these are experiments taken from this phase here. Okay, now I'm going to show you quickly a slip. So here is the friction coefficient, and then suddenly the friction coefficient goes down, and then the sample starts slipping. These are movies taken at 960 frames per second. So these are high-speed camera. Okay, now we look at the different phases, and we see that the energy flux, they are extremely small for the events in this phase here, in phase A, right? We are way below 0.5 megawatts per meter square. When we get in this part instead, where we increase the speed of loading, we get around 0.5 megawatt per meter square. And then in phase C, right, which is the most energetic phase, where we have the formation of melt and this big drop in friction, we go to energy which are in the order of a few megawatts per meter square, comparable to many other experiments. The interesting thing is that if we look at the acoustic emission, we see several features which are extremely interesting. Before the slip nucleates, the earthquake nucleates, we see, for example, foreshocks. We also see an increase in the noise in the acoustic emission. You see, this is the big event, the slip, and then before that event, as you can see here, the noise goes up, and we will have soon a formal analysis of this. Now I'm going to show you a video of what happens before the slip. And I would like you to look at this limit here, right? So this fundamentally is the old molten part, which was kind of weld together the bottom and the top sample. And then suddenly you can see that layer of old melt, solidified melt, breaks very slowly. You will see a foreshock here happening in a few seconds. Keep looking at the hand here. That's it. There we go. That was the foreshock. And then you see that this limit here is retracting slowly and eventually going smaller and smaller and eventually snap. Okay, what can we see from here? Well, using the high-speed camera, we can see the evolution of the melt during the slip. And that's an extremely interesting thing. We can also analyze the rupture length, and we can see that the rupture length can be fit with a typical equation, right, for a typical theory for that. We can, for example, look at the dimension of the patches of the welding patches, right? How they evolve in time before and during the event itself, and we can see that the patch decreases, becomes smaller, and then eventually, when it snaps, it becomes extremely small, and then as the slip goes on, then it becomes bigger as the melt grows back. Using acoustic emission, we can see also a series of events happening before the event. This is the entire loading of the sample. You see foreshocks here. You see a swarm of low frequency events just before the event itself. You see the slow deformation of the sample, which has been measured both by the sensor and by looking with the camera. But the most striking part that we found is that the acoustic emission really show very well what happens on the fault. We can see clearly that there is a gap of acoustic emission after the acceleration, the nucleation of the event, and this gap here, I'm talking about this. And then we see that the acoustic emission eventually comes back after a while when the sample is decelerating. And decelerating here. So the velocity is 0, then it goes up, then it stays up for a while, and then as it starts decreasing, then you do have a new boom of acoustic emission. The interesting part is this one, which is extremely interesting. So we can divide this in 4 parts. We do have a slow rupture with low frequency continuous acoustic emission. That was what I was showing you before the big event, right? This patch of melt, solidified melt that was breaking very slowly. Then we do have the dynamic rupture, right, where we have a lot of acoustic emissions. And then we do have a phase where probably our sample is completely lubricated, right, in here, where the velocity eventually stabilizes, right? And then we have a part where we think we have viscous braking. And here again, we do have loud acoustic emission. Now we can apply some theory. For example, we can apply the flash heating and weakening. And because I think my time is almost over, I think it is over. Please let me know. We can apply the flash heating and weakening, and we can find that the velocities, right, of weakening for plexiglass should be between 0.3 and 0.22 meter per second, which are these 2 lines here. Now, these 2 lines here, they correspond to this point here and this point here in velocity. And this point here is exactly where we see the acoustic emission ending. So we think that in this phase here, we do have the formation of the melt layer. And during this phase here, instead, we do have the maintenance, or the fact that this melt layer remains and stays there, right? And in fact, in this part here, the melt layer will grow eventually, and then it will maintain in this part here. The fact that the melt layer grows It's kind of highlighted by the theory of Nielsen and collaborators, 2008, which tells us which should be the time at which we have a continuous layer of melt formed. Now, applying the properties of PMMA, which maybe later we can discuss, right, how we get to this number, 10 milliseconds. And 10 milliseconds is pretty much the value of time where we see the maximum velocity achieved, and then where we start seeing this velocity maintaining constant. So the theory is that you do have a failure, formation of fracture, a lot of acoustic emission, and then the formation of a melt layer. The melt layer gets bigger and bigger. Now you do have a complete a molten surface at 10 milliseconds, supported by the theory of Nielsen and collaborator, right? And then on this phase here, fundamentally, you maintain that layer of melt, which eventually start cooling down and fragmenting. Fragmentation of melt is kind of theory that volcanologists use to explain, for example, eruptions. At the point where you start breaking up that melt, then you start generating new acoustic emissions, right? And at this point, the melt becomes kind of a break, right? You start breaking down and decreasing the velocity of the fault, up to eventually the fault stops and eventually reverses. And in nature, maybe in nature we do have this series of events, and maybe seismic waves. They kind of show different patterns according to what is going on. For example, if we do have melt forming, I guess that from that patch we might have less emission of seismic waves. However, the problem of nature is that we are always breaking a front, right? So you are always emitting seismic waves, while in our experiment we are breaking the entire surface. So we do have, we get to the boundary of the system. Well, the outlook will be, I'm almost at the end of my presentation. Now we do want to do some further work. We have to do it, and I'm very happy to do it. The outlook is to do statistical analysis and machine learning eventually on the precursors to try to forecast the lava earthquakes. Here we have an example again, right? The acoustic emission clearly show an increase in noise after this foreshock. Maybe there is something that tells us when these other events will come. And so here I show you a series of examples of experiments where there is this silent part, right? And the future steps are for sure to collaborate with the University of Oklahoma, because we have been funded by NSF. And the idea is to transfer the technology from ECoR, UT, to ROGA at the University of Oklahoma, in collaboration with Brett. His name is disappeared here, I'm sorry. With Brett Carpenter, this person here who is in Rome, and Zev Reches. And I'm very keen to see the results, what will happen with this machine. This machine is much, much bigger, and it would be very scary to be present at those experiments. I get to my conclusions. I think that ECoR is a cool and opens up new exciting opportunity to understand the feedback between the energy stored around the fault and how the energy is transferred from the fault zone into the fault, and the processes happening during and even before an earthquake, right? And we found in our experiment that acoustic emission, they really reveal when there is weakening and when there is strengthening processes. The question is, can we see that in nature? That's, I don't know to talk about with seismologists. And these acoustic emissions, they clearly mark changes in mechanical regime. If you want to know more about this research, please go and look at the paper, okay? And here I have some advertisement because we are looking for people. Thank you very much.